adjustments. So let's see what is the transfer function, frequency transfer function in the first place. Here, once you find the transfer function of a system in S domain, all it takes to convert it into a frequency domain as a frequency transfer function would be to substitute S equal to j omega in the original transfer function. So S will be substituted by j omega. S switched into a j omega. What it does, it converts the block diagram into a basically like a phasor block diagram, where x of s, which used to be any general time waveform, is now a cosinusoidal function. Here, x is no more step or ramp or any other kind of different type of a waveform, general waveform. It is only a cosinusoidal waveform. So x becomes a phasor, exactly the same way we did in AC analysis. H of j omega is the operator that converts that phasor into an output phasor. So the output is no more exponential or anything of that kind. It is simply a cosinusoidal. The frequency of the output is exactly identical to the frequency of the input. This is a steady state AC forced response. So, for example, if you apply an input amplitude of VIM with an amplitude of VIM cosine omega with a frequency of omega, T, the output waveform in general will be VOM, its own amplitude, VOM, cosine omega t plus some kind of a phase angle with some kind of a phase shift at that frequency. However, how can we deduce ratio of the output amplitude over input amplitude? This is defined as the gain. Well, simply the relationship of output amplitude to the input amplitude is VOM to VIM is the magnitude of y, this is y, magnitude of y divided by the magnitude of x, which is like output amplitude or amplitude of y divided by the amplitude of the x, the input. This ratio is called the gain, which is equal to the magnitude of h of j omega at a given omega value. If omega was a constant, which we did it in AC analysis, we took a fixed frequency and we analyzed it, then you're going to get just one number. But if omega is open, like a frequency, anywhere from 0 to plus infinity, then h of j omega, the magnitude of h of j omega, in general, it will be a function of omega and the system parameters, the content of the system. Similarly, the phase angle between output and input, here, this is the picture of the phase angle. X is VIM, angle 0, that's the first one. Y is VOM, angle theta, which is an angle which shows as a lagging angle. The angle of output phasor with respect to the input phasor, defined as theta, would be the angle of the function, h of j omega. Again, both this ratio, the gain, and the angle, phase angle, excuse me, both will be, in general, a function of frequency, omega. So a plot of a graph or a plot of the output amplitude over input amplitude and the phase angle against the frequency. So I'm talking about then two graphs. One is gain, the other one is angle. These two graphs are called frequency response curves for the system. Now, here, the ratio, VO over output amplitude over input amplitude, so-called the gain. This is the gain. The gain will be the linear gain. It will be a unitless number, of course. Often the gain is plotted against the frequency, but in the both plot here, both plot diagram, for a special reason, instead of plotting the magnitude, we will plot 20 logarithm of that amplitude. 20 log of the magnitude of the gain is called the gain m of omega in terms of decibel, dB. So this is referred to as the dB in units of decibels. So 20 logarithm of the gain will be dB. So it is very important to take the 20 log, which later it will become obvious why we do that. However, for the angle against the frequency, we will simply choose the angle itself, linear. No logging will be necessary. So our choice in the frequency response will be, when we are plotting gain against the frequency, it will not be the simple gain. It will not be the h of j omega, but rather it will be 20 times the log of j omega. There is a reason why we do that. I will explain in a minute. But for the angle, we will just use the straight, the angle in terms of degrees as a function of the omega. So these two sets of functions will be plotted against the omega, the frequency as the horizontal. The choice of the axis for this plot will be, for both of them, linear against the logarithmic scale. So the scale will be logarithmic, but the vertical will be linear. In the case of the angle, the vertical ordinate will be in degrees, straight degrees. But in the case of magnitude, m of omega, the vertical will be in units of decibels. Excuse me, in units of decibels. For example, if h of j omega happens to be 10, gain of 10, then you will have log of 10, that's 1 times 20 dB. So the curve will start from there, from the up there, 20 dB, 0 all the way to 20 dB. But if for the case of the angle at a given frequency, the angle happens to be, say, 90 degrees, it will start from 90 degrees. If it was a negative, it would be a minus 90 degrees. The horizontal choice is going to be a logarithmic scale. Why it is convenient? The reason is logarithmic scale is a compressed scale. In other words, we will be able to show a long range of frequencies in a compressed manner, on one scale, very conveniently. We can accommodate all the data points on the axis. And here is how it works. We take the scale, horizontal scale, and we start defining what is, let's say, log of 1. Log of 1 is going to be considered like 0. Okay. Then log of 10 will be 1. Then log of 100 will be 2. Log of 1,000 will be 3. So if you check, every time that the frequency is increasing by a tenfold, our unit on the horizontal axis is incrementing by 1 scale. See, log of 1 is the 0. So this will be the origin. Log of 10 will be 1 here. Log of 100 will be 2. Log of 1,000 will be 3. So if you look at the spacings from each other, they will be evenly spaced in decades from each other. However, The disadvantage is you will never be able to show the zero frequency on the axis, on the logarithmic axis. Why we are unable to show the zero frequency? Because log of the zero will be minus infinity. So we will never be able to show. But we have a choice of showing a considerably low frequency on the scale. For example, the one that I drew in here, check. If I choose the origin on the x-axis as the beginning of 0.1 of a hertz, then 0.1, a decade over 0.1 is the 1. 1 will start right here, 1 unit up from 0.1. Then 10 will be another 1 up from 1. And 100, another 1 unit above the 10. So if you check, we will be able to accommodate with only 1, 2, 3, like 4 cycles, 4 cycles, 4 units, or 4 squares. We will be able to accommodate from 0.1 of a radian per second all the way to 1,000 radian per second. That is 10,000 to 1 ratio. So this process is called compression. So we take the frequency 10,000 to 1 scale, just compress it to simply 4 scales, evenly spaced scales, increasing in decades of frequency. Then you may ask, what happens, for example, to the numbers in between? Let's say, what happens to let's say 3? Okay, this is 1, that's 10. Okay, so this is a whole unit. Log of 3 is approximately 0.47. 0.47 of the scale. So in this scale here, if you divide it into 10 parts, 0.47 is going to mark 3. So 3 will be right there. Almost halfway between 1 and 10. 2, log of 2 is going to be 0.3. 0.3 will be here, about 30%. This will be 2. And as you keep going up and up, you will see that the scale will get more and more and more and more compressed. For example, log of 9 will be almost very close to the 10. And from this point onwards, all the cycles will repeat. For example, if 3 is in this position here, in the 1 to 10 scale, 30, which is 10 times over, will be exactly in the same location on the next scale here. This will be your 30. 30. So that is your 1. This is your 1. This is your 10. If 3 is in that position here, let's say, if 3 is in this position that I marked with a dot, then 30 will be in the next scale here, in that position, because 30 is a decade over the 3. And the 300 will be here, in the same position, scale-wise, in the next square. So in this way, you can compress the information, and you can go and find the appropriate frequency that you are looking for simply by looking at the numbers of divisions. So log papers, such graph papers, are called linear, logarithmic scale. And these graph papers are available. So often in simulation, when you're doing the frequency response, the system will call what kind of a scale do you want? Do you want a linear scale or linear log scale? Now, when we're doing the both plots, definitely go for logarithmic scale. The top will be linear, which is both linear, and then the horizontal will be a logarithmic. It would be impossible to use a linear and linear scale successfully for frequency, because you can never in a linear scale show 0.1 radian and 1000 radian. You can never catch it within the span of the axis. The reason is 0.1 compared to 1000 is 1 to a 10,000 ratio. So if you choose 0.1 even as a 1 millimeter, the other one is going to be tens of thousands of millimeters. That will be 10 meters away from your choice. So it will be impossible to grab it. Therefore, that is why we use linear logarithmic scale, and we spare it for frequency presentation, because frequency has generally a very wide range. Okay, so let's see what we have so far. I explained the transfer function, our traditional, which is output Laplace over input Laplace. It comes always as a function. But if your waveform is a sinusoidal, sine drive, a sinusoidal drive at the input, then the output is going to be a sinusoidal also at steady state when the transients expire. And that can be found, the output amplitude over input amplitude, which is gain, can be found by substituting S equal to j omega in the transfer function. So convenient. And the angle of output, phase angle of the output, can be calculated from the transfer function simply by figuring out angle of h of j omega at that frequency of interest. And both of them, gain and frequency, both of them will change with frequency. Angle and gain both will change with frequency. So both plot, however, is the term given to a unique frequency response consisting of a gain and the angle. The angle versus the logarithmic scale frequency is called phase response, which we'll discuss that, phase response. The magnitude, however, is not just a straight plot, but rather 20 logarithm of that will be plotted. And that is called the gain response. Also, when you 20 log something, you compress it. Because sometimes, amplifiers have a huge gain, like 100,000, okay? So for 100,000, excuse me, 100,000, log of 100,000 is 5. So 5 times 20, it will be 100. So an amplifier with a gain of 100,000 will begin from 100 decibel. Now, the reason why we are logging is this. Why do we log the gain, and do we just leave the angle as is? The reason is often you may have two cascaded transfer functions together. So you have a transfer function, for example, of say T1 of j omega, followed by a second one, T2 of j omega. Here. So you may have a situation where you may have T1 of S followed by a T2 of S. And you want to know the net response. X of S, and then the last one is Y of S. Okay? Now, Y of S over the X of S is going to be the product of the two transfer functions, T1 of S times T2 of S. Well, this is the reasoning for that. Simply the output from number 1 is T1 multiplied by X, here, X times T1, then the output from number 1 becomes an input to number 2. So x as T1 multiplies T2, that makes the output the plus. So one transfer and the other one transfers the transfer of the first. Now, if you notice here, in terms of the frequency response, T1 of j omega then needs to multiply T2 of j omega, x and the y. So y over x is therefore T1 of j omega times T2 of j omega. Now, if you want to graph the overall gain, magnitude of T1 of j omega, T2 of j omega, you have to work out the complete transfer function of the product. So these two functions may have omega contents, and when they multiply, you need to sit down and work out the complete transfer function in order to make a plot of the transfer function against the frequency. However, if you look at the 20 log of y over x, this will be equal to 20 log of T1 j omega, T2 j omega. Okay. So the magnitudes of each one can be calculated and multiplied together. However, we know what happens to the log of products. Log of A and the B is equal to log of A plus log of B. So this will come to be 20 log of T1 of j omega added to 20 log of T2 of j omega. So notice that the combined transfer function, the 20 log of the combined transfer function, is equal to the sum of logarithmic plots of individual function. So if you have one function plotted graphically, for example, if this happens to be, say, T1, okay, and the other one happens to be like, for example, here, T2. If this is T1, assuming the two slopes are identical, the graphical addition, and this is the 20 log of either one. If you add these two functions together, it can be done very easily, especially if they are segments of lines, either horizontal or at an angle, well-defined slope, well-defined negative slope, which standard transfer functions tend to have that fixed slopes. So I can graphically add these two functions together. It's very easy. Simply all you have to do, the sum of the two will come up to the following. Here, go segment by segment from here all the way to this breakpoint. Green is 0, red is 0, so the resultant will be 0. Then from here all the way to here, this particular breakpoint, each one has a breakpoint of its own, omega 1, omega 2, there. The sum of the two functions will be the sum of the red, which is 0, added to the slope. So it's going to be sloped exactly at the same rate as the green one, up to here. But from omega 2 upwards, from this point upwards, to the right, notice that as much as the green is adding, if the two slopes were equal and opposite, as much as the green is adding for every increment of the frequency, the red is decreasing at the same rate. Therefore, the line is going to stay in this region as a constant. So what you see in here will be regarded as 20 log of T1 multiplied by T2. Because addition in the logarithmic scale, addition of the log is equivalent to the product of the function. So it's the logarithm of the product. Yes, of course you know this, that the log of A, B is log of A plus log of B. That's the fundamental rule of the logarithm. So the greatest advantage of this logarithmic concept, plotting the logarithm of the gain against the frequency and scaling it with a multiplier of 20, that is just the multiplier of the choice, 20, just standard. The addition of these logarithmic verticals together is equivalent of multiplication, logarithm of the multiplication. So the outcome in here, let me show you the brown curve here. This is the outcome. The brown is the outcome of the green and the red. The brown curve is therefore the logarithmic plot of the product of two. Here I wrote it, 20 log of T1, T2. While each one is only 20 log of T1, and that red one is 20 log of T2. 20 log of T2. Okay, so why we go for the logarithmic vertical scale? It should be clear for you at this point. Because if you do each one individually with a log scale, each gain you present it with a log scale, then simply when you have multiple of the cascaded stages, and you do the graph of each one, each block individually, in the end, if you want to know what is the gain of the whole block transfer from in to the out, you will simply graphically add linear segments to each other. It takes a little practice to gain skill in how to manipulate this summation. You will learn that throughout the course. This is maybe the first time that is introduced to you, but it is waiting for you in the next trimesters. Your filter design professor will do that. Your control engineering professor will do that. Exactly the same thing. And it is a very handy tool for actually getting insight into how the overall response is going to behave. However, this logging of the gain, which allows us to multiply, is completely relevant. But for the angle, actually, you don't need to get the logarithm of the angle. You never do that. You will simply plot angles individually. For example, if you had, instead of gain, let me erase this. Here, if you have the phase angle here, if this was the angle of T1, angle of transfer function T1 of j omega, for example, it was rising from 0 degrees to 90 degrees at a given slope, at a given two specific frequency here, omega 1 and omega 2. And you had for instance, the angle of the other one here, going all the way to here, and then going down at the same rate, then becoming, say, minus 90 degrees, minus 90 degrees. This will be the angle of transfer function T2 of j omega, okay, at a separate frequency, omega 3, omega 4. Okay, so if you could present the angle of T1 of j omega with linear approximations like three-piece line, and we could present the phase angle of function T2 with three segments, with the three line, then the overall angle theta total would be theta of the angle of T1 plus the angle of transfer function T2. So this is the angle of T2, that's the angle of T1. You need to add them, and this would be the overall angle. So you have to basically add these two curves together. Again, just a little practice will help you to do that. For example, you have to break the frequencies section by section here. Up to here, they are all 0 degrees, so nothing. From this point all the way to here, that is omega 3, it seems that the green is adding. So we will go up exactly at the same pace, at the same rate, up to here. At this point, notice that if the slope of that is equal opposite to the slope of that, then the angle is going to stay constant all the way to here, all the way to here. Then the green one has 0 rate, so it's not adding anything, but the red one does go down with that rate, so you will slope down at the same rate as the red one, and then from this point onwards, there is no rate of increase, so it is going to stay flat. So we can conclude that the output phase angle, the total phase angle, is going to follow this brown track. There it is. So the function is going to look like angle of T1 of j omega multiplied by T2 of j omega. This total angle is going to have that kind of a shape. It's going to be 0, then it will take off at a frequency of omega, from frequency of omega 1. Then it will kind of, go flat at the frequency omega 3, determined by the lower one. It will stay like maximally flat, or kind of, peak to a maximum. And then it will start going down, and eventually it will become a 0 degrees phase shift. Of course, this combination shows that it must be a leading in phase, because phase angle is positive, and then becoming 0. We can estimate what the maximum will be. Because the angle that it broke was in the middle, we can really call that 45 degrees. So we are estimating our phase angle is going to shift from 0, of course, much smoother than a straight line, from 0 and then slowly rising, peaking, but not exceeding about 45 degrees, and again going back to the 0 degrees. So this particular combination of the transfer function with their responses are creating a predictable overall phase angle. I promise you that you need this intensely in the control engineering when you start doing the real design frequency compensation. compensations, and so on. Often we want to know where to put that maximum in order to shape frequency response and to get a system stable. That is an art by itself. Only control engineers can do that properly, and their tool is Bode plots. Bode plots. Gain against frequency, in fact 20 log of gain against the frequency, and phase angle against the frequency. So here, let's focus on what the whole thing is. In the next part, when I'm talking about the Bode and the purpose of the Bode plot. So in part one that I talked about, we understood what is the frequency transfer function. Now, we are extending the concept of that Bode to blocks that are cascaded. Therefore, the frequency transfer functions cascade. And in order to get a gain, overall gain, the best is to get the log of the first one and log of the second one and add them, of course, with a multiplier of 20. And when you add, adding log of A to log of B, the outcome, the product, the result, will be the log of the product, which is the product of the two functions. And that's what you need for overall gain, product of the two functions, gain 1 times gain 2. Same thing for the phase. For the phase angle, however, it is not necessary to take the logarithm of the angle. You will simply need the phase, because if you're multiplying these two together, watch here, if this has a magnitude of P1, an angle of theta 1, and that has a magnitude of T2, an angle of theta 2, when you're multiplying, see, T1, T2 is multiply, but theta 1 plus theta and theta 2 is add. So the overall is T1 times T2, but the angle is theta 1 plus theta 2. See, this is a product that is a sum. That's why we don't need to get the logarithm of the angle when you're plotting. Just plot the angle straight as a linear scale against the logarithmic frequency. Okay, so this lays the ground description of what is Bode plot, why we do it that way, and we are going to learn how to utilize some standard transfer functions in order to, do a composite drawing. Now, let us take a look at the standard transfer functions. Let me keep track of time here. Okay, so let us look at the standard transfer functions. I have, it was around 4 to 5, I did send out the lecture 4 3-page document to your email address, which is the topic for today. So far I talked about page 1 of the 3. I hope you got it. But again, I could not post it on the Blackboard because the capacity is full. And unfortunately, my documents are picture documents. It is my fault, I know. There are picture documents and I'm posting them as pictures, and it takes a lot of capacity. Each page takes about 10 megabytes. So once I run out of capacity on my Blackboard, I don't have any other tools like PDF converters in order to convert them to PDF. So that's why I did standard picture. So I tried to send them with an email them directly. So attached as file. I use my Yahoo email. Unfortunately, my school email doesn't work with my computer, or actually it's the reverse. My computer doesn't work with that. So I tried to attach the 2 pages to the Yahoo email. Unfortunately, the Yahoo's capacity is 20 megabytes. So it just takes barely like 2 pages. Actually, it's 25 megabytes. So with the Yahoo, I can send only 2 pages at a time, the bottom line, with picture documents. Therefore, I had to make it 2 consecutive emails. Make sure that once you open one first email, go to the second email to find the page 3 there. Page 1, 2 is in one, page 3 is in the second. So I'm sorry about the inconvenience, but there isn't much that I can do at this point. Hopefully the summer will give us some opportunity to come up with a proper setup. I don't have it right now, and I cannot go and find at this point. Okay, so let us take a look at the standard transfer functions here. Transfer function, TF, just to shorten it. Number 1, I called it case 1. So you have everything, you don't need to draw, it's just for reference. When you have an h of s, case 1 here, an h of s equal to 1 over s. Okay, how do we convert that to a frequency transfer function? You simply substitute h of j omega is 1 over j omega. And you create that into a magnitude and an angle. So magnitude is 1 upon omega. The angle is minus 90 degrees. So this is our theta. And this is our magnitude. Therefore, the both will be equal to m of omega. Both will be m of omega equal to 20 logarithm of 1 over omega, which is minus 20 logarithm of omega, where omega is the frequency. But the theta is straight 90 degrees. A transfer function of 1 over s is referred to as a single pole transfer function, with the pole being in the origin. Remember what was the definition of the pole. The value of an s that turns the transfer function infinity is called pole. In other words, you find the poles by setting the denominator equal to 0. This is the denominator of s. It's one term, has just one term. So technically they show them as, if this is S plane, that's the j omega, and this is the sigma, this is where it is. Pole is shown with a cross, with an x, right in the origin. How do we interpret those functions as an angle? This one and that one. Here is the presentation. So I chose a scale for you, omega, and this is the m of omega in decibels. And I chose an axis, some kind of a scale. I wish to call the lowest as 0.1 of the radian, then the next scale will be the ones. In the next, the tenths of the radian will begin. The next, the hundredths. And the next one, the k's. 1K. So if I want to find out, for example, what is 20 radian per second? 20 radian per second. it should be in this range between 1 and 10, and 20, or actually go for 2. Say I want to figure out, the 2 radian per second, 2. Log of 2 is going to be about 0.3. So what is the meaning of 0.3? 0.3 means 0.3 units of the scale. This is your scale. 1, because that is equal to log of 10. So log of 10 is 1. That's one scale of logarithmic scale. So 2 is going to be a 30% here, 0.3. So lengthwise, if 1 is 10 centimeter, then 0.3 is going to be 3 centimeter on the scale. 3 will be 0.47, say 0.5. Then it will be almost in the middle of the scale. 4. So it goes 2, 4, etc., etc. So that is the way it is. Now, graphing it. How do we graph this? Here. Check the function itself. This is the easiest of all. Yep. If you put omega equal to 1 in this equation, the outcome will be log of 1, which is a 0. So it's going to pass from here. Okay. If you put 0.1, what will happen in the omega, like a decade below that, 10 times under. 0.1 will be 10 to the minus 1, so minus comes to the front and converts this to positive 20. So the positive 20 will be right there, 20 dB. What about 10 times? If you make this 10, this will be log of 10 is 1, so you get minus 20 dB. Minus 20 dB will be symmetrically down here, minus 20, just under the 10. So if these scales are identical in length, that is symmetrically above this one, then of course, if I continue, we are going to get a straight line like that, going down with a constant slope, with a fixed slope. Let me get a better line. There you are. And hopefully a better one. Okay. So this will be our m of omega for the m of omega for 1 over s. A function equal to 1 over s. It will be a straight line. I want you to notice, and it is extremely important, is the slope of this line. The slope of that line, and always it will be the case, is minus 20 decibels per decade. It means per every tenfold in frequency, as you increase the frequency by tenfold, the angular frequency, radian per second, as you increase the frequency by tenfold, you're going from 1 radian to 10 radian per second, 10 radian to 100. The gain keeps dropping by a 20 dB. So gain drops at a constant rate of 20 dB all the way down, no matter how high you go in the frequency. Negative 20 dBs speak of numbers that are less than 1. So remember, log of fractions are negative because fraction is less than 1. So it keeps going up and up. You can, from the graph, you can read what will be the gain at 100 radian per second. Here, that naturally will be minus 40 dB. Minus 40 dB. That's a pretty low gain attenuation. Minus 40 dB means minus 40 is 20 log of what? If you calculate, this will be log of that number will be equal to minus 20 and excuse me, minus 2. And that means A, it's got to be 0.01. It is 100. 100. Not even 1/10. See, this is a gain of 1 because log is 0. Here, omega equal to 1 gives you a gain of 1. So at 1 radian per second, if it is 1, at 100 radian per second, it's going to be 100. It attenuates. Okay, this is the Bode plot or Bode plot of 1 upon S or 1 over K. So what happens to the angle? They come together. So we will utilize identical scale. Omega, here, linear. That one is also linear, but it is already log. The numbers are log. Otherwise, it is linear. So if this is 20, that's a 40 dB. Here, it's logarithmic, so we go to 0.1, and then we get to 1, tenths, hundredths, and 1/k, etc. Okay, the phase angle. The phase angle, if you notice there, is permanently 90 degrees. 90 degrees lag. That's a lot of phase lag. And it is independent of frequency. So 1 over S, whenever you see that, there must be an inherent 90 degrees phase lag at the output. So if you put a sine wave, let's say if you put a cosine wave at the input, it will lag by 90 degrees. A sinusoidal shape will come, which is the same cosine shifted to the right by 90 degrees. So here, regardless, this is your k. Regardless of the frequency, it is a permanent 90 degrees. So this is the case 1 standard transfer function for a pole in the origin. Now, I didn't do it here in the paper, but what if there was an additional gain of 100 here? Let's say gain of 10. There was an additional gain of 10. What would you do? Generally, what is the Bode plot of numbers, constants? Not poles, not zeros, just constant. It is simply 20 log of that constant. That's what it would be. So you will go and take 20 log of 10, which is just 20, and then you will add that 20 to this line. So that means simply you will take the red line and you will shift it up by additional 20 dB. So this point on the 0.1 radian per second will move there. This point will move into the 20, and that point will move here. Then you will get that line. If you had 10 over S. So simply the constants will cause the magnitude curve to shift up, or maybe even shift down if it was less than 1. For example, instead of 10, if you had a 0.1, log of 0.1 will be minus 20 dB. So you need to take that line and then shift it down by minus 20 dB. So that point will move here, this point will move there, that point will move 20 under, but it will stay same shape. So that is how to deal with the constants. At this point, when I'm doing my standards, I'll try to avoid the constants because I don't want to make it more complicated. So simply, we just look at the classic functions, 1 over S. Underneath is this. Now, that's the phase angle. Now, let us take a look at the zero, case 2, a transfer function with a zero. What will happen? So let me erase this. I can use that. Case 2, h of s is equal to s. Now, that means your transfer function has a zero at 0 point in the origin. So if you look at the whole zero diagram, the S plane, J omega and sigma, and this is the S plane. Location of that zero will be here, right in the origin, in this set. Okay, what is the transfer function? We will simply proceed the same way. H of J omega will be simply equal to J omega, which it has a magnitude of omega and an angle of 90 degrees, a positive 90 degrees because of the J. So what it does, if you apply a sinusoidal input to a system that has a zero, a sinusoidal input, it's going to give you an output which will cause the phase to shift 90 degrees leading with respect to the input. That's the meaning of this angle. It will lead by a fixed 90 degrees. How does it look on the graph? How will it look? There is the omega. This is the magnitude. Again, let's choose a scale, 0.1, ones, tens, hundreds, and thousands. Okay, just by numbers you can show. The m of omega will be equal to 20 logarithm of omega. Much noise. Okay. It will be 20 logarithm of omega. So simply try numbers there. Put omega equal to 1. That will be log of 1 is 0. So it will be right there. Put omega equal to 0.1 here. Log of 0.1 is a minus 1, so minus 20 will be here. Log of 10 will be 1, or with 20 dB, positive 20 dB. And so on. But you will notice that all these 3 points will be collinear. So a line will pass through all of them, a straight line, as you can see. That is m omega of 1 upon s. By the same token, it's exactly opposite of the pole in the origin. This line will have a slope of positive 20 decibels per decade. Positive 20 dB per decade. About the angle. The angle response, however, here, by the same frequency, 0.1, ones, tens, and the hundreds, etc., will be a permanent 90 degrees. So you will have like a 90-degree shift. Theta, just positive 90 degrees, and it will be a positive degrees. It means it will be V. So if to that transfer function, to that h of s, if you apply an x and you get a y out of it, if the x phasor is shown this way, horizontally, then the y phasor will be that way. Of course, the length of the y, magnitude of the y phasor will change depending what the frequency is, because it's increasing, the gain is increasing the frequency, but the angle will remain a fixed 90 degrees. So it will always be leading by 90 degrees. Generally, S should be associated by d by dt operator. Whenever S multiplies a function, it differentiates it. It creates a derivative of the function. For example, if you have a f of s and you look at the s times f of s, where f of s is the function, f of s is the transform of a function of time, then s times f of s will be the df by dt of that function. Opposite of that would be the integration. If 1 over s multiplies a function, actually the outcome is it converts the function into integral. So it will generate the integral of the function. Now, this will be the response of, therefore, a 0 in the origin, which is, again, a very popular one, and it is called a differentiator, or differentiator, just a plain differentiator. Okay, so let me keep track of time. Now, let us get into other variations. There is a possibility that now we can get a function of s, or h of s, with pole, let's take it as a real pole, with a pole on the real axis away from the origin. And also we can have a 0 that is located on the real axis away from the origin. Let us see how the transfer functions will change. Those are the other two cases. Okay, so let me erase this. Case 3. Single real pole. Okay. The normalized function h of s is going to look like omega o s plus omega o. Omega o often is called the cutoff frequency, of course in radian per second, or just the break frequency, or break frequency, or sometimes just corner frequency. Corner frequency. There are many names given. What does that mean? The pole value of s that will make the function infinity is located at minus omega o. So in terms of the pole zero diagram, here, sigma and the j omega, it's going to be located here, minus omega o. This is the pole position of that transfer function. About the response of that transfer function, how do we translate them into curves? This one is a little bit more involved. Number one, we have to, and why, if you may ask, why there is an omega in the numerator? Well, because we are going to come up with normalized transfer function. If there wasn't any omega in there, you have to create that omega. Let me give you an example. Look at this. What if you had 5 over s plus 20, right? So we are going to convert that to a standard. I'm going to write this 20 over s plus 20. So look at the denominator, copy that, post the 20 at the top. But I can't write 5 in here, because if I write 5 there, the balance will be disturbed. So I'm going to write 5/20 here. This is the standard. Standard. 5/20 is a number, quarter, 1/4. Number. If you want to get the mode of constants the same way that I told you, simply you take 20 log of 1/4. 20 log of 1/4. You go figure this out, it should be a negative number. And that negative number, that constant, when you add to the other graphs, it will cause either, if it's a negative, the graph to drop, to shift down. If it is positive, the whole graph will shift up. Okay? So don't worry about that format. We're just studying the normalized function. You know, like omega O, shape it in that form. Okay. Now, we have to break that function into algebraic form. So allow me to erase this to gain some space. Here. H of j omega, magnitude of h of j omega, is going to be 1 over square root of 1 plus omega over omega O, the whole lot, squared. Oh, this is the magnitude of that function. How did I get that? Well, the top is a number, dividing the denominator. Just put j omega. So magnitude of top would be omega O. Magnitude of that would be square root of omega squared plus omega O squared. Okay, so take the omega O underneath, or factor out omega O. We'll go into that form. Then it cancels from top and bottom. You end up with that. This is a pretty normalized function. Notice that omega is a radian frequency. What's the difference between regular frequency, like common Hertz frequency? It's just a 2 pi. So you can reuse all of these equations simply by writing, instead of omega, just f over f cutoff. All it takes is just a 2 pi. So the ratio doesn't change anyway. Whether you write actual frequency, Hertz frequency over f, or you write it omega over omega O. The weight of the function is not going to change. It's the same thing. Okay, so we got that. Now let us take a look at the angle. The angle of that function, theta, which is equal to angle of h of j omega, will be equal to angle of top, which is non-existent, 0, minus angle of bottom. Angle of bottom is equal to minus tan to the minus 1 of omega over omega O. There you are. So we got now pretty much a kind of a series functions here. How do we sketch these functions? Okay, here is how to do that. If you look at the top one, the magnitude function, whenever omega is much, much higher than omega O, like way higher than omega O, generally the square term is going to dominate over the 1. So if you delete this 1 condition, omega is much, much greater than omega O, under the radical becomes a perfect square. If you square root that, omega O will go to the top, omega will stay at the bottom. You'll get omega O over omega, 1 upon omega. Okay, so you will see that the relationship between h of j omega and the frequency will be an inverse relationship. Very similar to 1 over s, where for s we got an omega, j omega. So at high frequencies, this thing is going to work almost like an integrator for the higher frequencies. Now, the plotting of this function. Here is how to plot them. Let's learn. Okay, you choose your axis, label them. Let's say this is my 0.1s, and this is my 1s. This is my 10s, and the 100s, and the Ks. Okay. And that is my scale. Let's say this is 20 dB, and that is a minus 20 dB, and then 40 dB, 60 dB, etc., etc. Here, minus 40 dB, equally spaced. Here is how to draw the Bode magnitude. Okay, I think it's 8:15 now. Let us take a 13 minutes break, and we come back at 8:30. Okay, so back 8:30. Let's come back then. Okay, and then we will do the complete analysis. Church.